Okay, I guess we'll get started. So I'm going to today cover three things. One is I want to talk a little bit more about duality in the Fourier transform because there was a bit of confusion last time, and I'm not going to go exactly into what I posted on Piazza. You should read that, but I want to talk a little bit more about duality. And then I'll go into the properties of the Laplace transform and then get started with the discrete Fourier transform. And then in the next class, we'll talk about the fast Fourier transform, which is kind of a special case of the discrete Fourier transform. And with any luck, we should be able to do that. And then the last ninth lecture, we'll do the Z transform. And then we'll be done with transforms and get into control theory. Okay, so I wanted to point out the what is intuitively going on with duality. So let's just look at the Fourier transform. Where we define xj omega equals and then the inverse transform is xt equals 1 over 2 pi integral minus infinity infinity x j omega e to the j omega t d omega. So what you see is that basically, other than this factor of 1 over 2 pi and this negative sign over here, you have a very similar form. They both are integral from minus infinity to infinity, and you just have, so that's mathematically speaking, that's the reason why the duality works, where we can look at basically xt and xt and x of j omega and x of j omega. Okay, I'm leaving out the negative signs and just say these look formally similar. The other way of looking at it, and which has a bit more intuition, I think, and it's interesting, is that we've already seen that if you have a single rectangular pulse in the time domain, so this is time over here, and this is the amplitude over here, so this is the value of xt, then in the frequency domain, this looks like this. We have in the omega domain, what we have is a sink, which is essentially the sine x by x form over here. Okay, actually it's sine omega t, but it's sine omega, but anyway, it doesn't matter. But the form is that the pulse becomes this the sink function. What we can do with duality is that we can change the basis. So we can say that if this is time, and we're forgetting the 2 pi for a moment, then this is what it looks like in frequency. Okay, so now this becomes x, and this becomes capital X. So in other words, if I have a function which in the time looks like a sink function, like so, then in frequency it's going to look like a pulse. What does it mean to look like a pulse? It means that there is some what we call a frequency band, and the pulse is completely contained, and the energy is completely contained inside this frequency band. Okay, so that's the meaning of a frequency band. So we talk about, in networking, we talk about bandwidth all the time. Okay, bandwidth means the width of this band. Okay, and notice that this band over here is both positive and negative omega. It means you have phasors going in both directions. But ignoring that for the moment, this is the sort of the width of this band. Okay, it's the frequency band. Yes.
When you consider the second graph with the time as the basis,
yes,
and when you are transforming it to omega basis,
right,
you are applying it Fourier transform on this graph, right?
That's right. I'm going from basically, I'm doing the Fourier transform like this. That's right, on the sink function.
And you were telling you will get back that pulse.
I'll get a pulse in the frequency domain.
Okay, so how is it different from inverse transform?
It is, well, it's not the inverse transform, because we're going from time to frequency. We're still going from time to frequency. Inverse is going from frequency to time. We're still going from time to frequency, except that the shapes are preserved. This is not time, and this is not frequency. Okay, we're still going from time to frequency as a Fourier transform, except that now we have this, we are giving now some meaning to what does it mean to have a frequency limited pulse. Okay, we can think of a time limited pulse. It's 0, it goes to 1, it stays at 1, it goes down to 0. Here what we're saying is that there is no energy. We say there's no energy except in the range plus minus, let's say this is omega naught by 2, so the bandwidth of this would be omega naught. That's the bandwidth. So when you talk about frequency dial, on your FM dial, you tune your C word to a particular frequency band. This is the band we're talking about. There's no energy outside of this particular band over here, and so that's the bandwidth. Okay. And when you talk about information theory, which will be later, you'll see that the width of this band is very important. It tells us essentially how much information can be sent on this channel, on this communication channel. Okay, the bandwidth turns out to be the critical piece of information that tells us how much information can be sent on this channel, which has a particular bandwidth. Okay, and we talk about a bandwidth of a wired link. So when you see an ad from a broadband carrier say, "Oh, we'll give you 2 megabit per second bandwidth." Okay. They're abusing notation, so we really don't have a band there in some sense, okay? Or they're not really talking about the bandwidth, they're talking about how many bits per second they can carry. It's 2 megabits per second, which is actually information content and not really bandwidth at all. But anyway, I'll come to that when we talk about information theory. But for now, I want you to get a physical sense of bandwidth. So what does it mean to have a band of this? What it means is in the time domain, we're going to have a sinc function. We're going to have a pulse which has, it goes from minus infinity to infinity, okay? And at 0 time, or before 0 time, actually we have some value over here. Now, of course, this makes a signal non-causal, in the sense that we always say that time 0, we have 0, there's 0 before time 0, but in this case, we actually have time going in all the case. So what we really have doing is we're going to actually time shift it. Okay, we're going to time shift this by some value so that we actually have the 0 being over here, and then we'll have the pulse over here. So this becomes causal, and then what we're going to do is we're going to ignore this part over here. Okay, when you do that, what happens is that this pulse, which looks nice and clean, is going to not look so clean anymore. It's going to have these kind of a shape like this. So it's going to leak out of this band over here, and this leakage is what's called something called a sideband, or it's called the lobes, and so on. So when we talk about any signal when we're doing signal processing, you'll quickly learn that we never have a rectangular pulse. We actually always have sort of this little bit of extra energy that goes on the side, called the sideband. Okay, so we have what's called the center frequency. That's the center frequency, and then we have a little bit of slop on the sides, and we want to make sure that the slop on the sides isn't too much. Okay. And that's reason is because we never have eternals. If you had a perfect sync, just eternal, yeah, that would work, but it's not eternal, right? So it's going to go for a certain period of time, then it's going to stop, and then because of this, we'll get this sloppy shape over here, okay? Similarly, if we take some real energy signal, because sloppy, we can put what's called a band pass filter, so we're going to remove almost all the energy outside of it, and the shape inside will be sort of rectangular, and the time domain which will look sort of like a sinc function. Okay, so we have this sloppiness, but the sloppiness is not because we don't have good electronics. The sloppiness is mathematical. We cannot have eternal functions. Okay, we do not have infinite time. We do not have infinite. So the band is always going to be sloppy because we never have infinite time signals. So that's the because of duality. Okay, so this is duality, sort of mathematically speaking. This is duality from the perspective of engineering and building actual circuits. Okay, and so when we do the time shift over here, by the way, this is just x t minus t naught. If this is going to be t naught, and then we just use the time shift operator to determine what the appropriate frequency is going to be. It will be e to the minus j omega. T naught will be a multiplication, so we're going to have something multiplied by a constant factor, actually. It's going to be. Okay, any questions about this over here? So we can do this for any time. For the Fourier transform, we can do it for any pair. We can take anything in the time domain, go into frequency, and then say, okay, if that were in time, this would be what it would be in the frequency. So we can swap sides basically in the Fourier. That's why it's very beautiful. The issue is this 1 over 2 pi factor. And so you have to make sure that, but that's just a constant multiplicative factor, and it works nicely for symmetric functions because then t and minus t are equivalent. Okay, for asymmetric functions, where t and minus t are not the same, it's a bit messier. But for this kind of nice symmetric function like this, everything works out well. Okay. So any questions about this over here? Okay. Oh, and I should point out the one function which is very nice, because the time in both sides it looks the same, and that's the Gaussian. That's a Gaussian function. So essentially, e to the minus t square is basically the Gaussian function, right? If you remember your Gaussian function, it's basically x of t equals 1 upon sigma root 2 pi integral. Sorry, what am I doing? E to the minus. Okay, so t minus, okay, I want to write mu over sigma square. So this is the way we normally write the Gaussian. This is some factor, and this for a Gaussian probability distribution. But the sigma root 2 pi is just to make sure it adds up to 1, so we can get rid of that. And let's say it's 0 mean and standard deviation is 1, in which case it just becomes e to the minus t square. Okay, so e to the minus t square is really the Gaussian. Okay, if you take away all the other frills, e to the minus t square is Gaussian, and it turns out that the Fourier transform of this looks like e to the minus omega square. Okay, I'm leaving out some factors, so more or less it looks like this. So a Gaussian pulse, a Gaussian in the time domain basically goes to a Gaussian in the frequency domain as well. So, and again, leaving out the constant factors and leaving out where it is, intuitively this is a very nice function. It kind of retains its shape as it goes from one domain to the other domain. And that's actually worth trying out for yourself to make sure that when you put over here e to the minus t squared, you'll actually get a Gaussian as well. It's a pretty easy thing to figure out. Okay, any questions about so far? Okay, so I'll stop here with the Fourier, and I'm going to go back to the Laplace transform. And last time we talked about some properties of the Laplace transform, and I'm just going to remind you what the Laplace looks like. And many of these properties just come. So we say x of s is equal to integral minus infinity to infinity x t e to the minus s t dt. So what we have over here is that we are multiplying the function value over t with the formal parameter, in this case st. S is going to be a complex number. X belongs to the complex, and it's equal to sigma plus j omega. That's the standard notation that we use, where the real part of s, real of s equals sigma, and that's where we have. So we have a complex plane, and we have a function of the complex plane. X is a function of the complex number s, and defined in this way. So this is what we did last time. Based on this, we have some properties that kind of are immediately we get for free, basically. So I'm just going to, and these mirror those of the Fourier transform, and that's because the Fourier transform can be viewed as a subset of the Laplace, in the sense that when the region of convergence of S includes the vertical axis, the j-axis, then the Laplace and the Fourier are the same, okay? Because basically we can then do the inverse transform along the j-axis, and then we get the Fourier. Okay, so linearity says that if, and so we'll just assume that x1t has the Laplace transform of x1s and x2t has the Laplace transform of x2s, where these are going to be, that's given. So linearity basically says that the transform of ax1 t plus b x2t, the transform is ax1s plus b x2s. And this follows directly from the definition, because just like the Fourier transform, if you have constant a, you can pull it out, and the integrals sum up, so these things sum up, right? So it's straightforward. So any questions about that? So, and that's a very nice property of Laplace, which means that if when we'll do an example of solving a system using Laplace, what we do is we just look at each term, and we can take each individual term and do the inverse transform, one by one, because of the linearity property. Okay, so the second one is time scaling, and in the notes in the table the notes are opposite. So here it's just saying an expansion in time scale compresses the frequency scale. What I really should have said is a compression in time scale expands the frequency scale. So same mistake as last time because of the factor, but basically what we're saying is that x of at corresponds to 1 over a x of s over a. Okay, so that's your time scaling over here. And again, this is very similar to the Fourier. And I'll just write down frequency scaling because it's basically the same form. 1 over a t over a, okay, x of t over a, it corresponds to x of as. So now one question I had, one question that came up in the Piazza about the Fourier transform and the time scaling was, can we scale by a complex number, by j? Okay, and what happens when you scale by j? So I actually spent quite a bit of time going over this, because my reference, and I'll show you this book, is this book by Kraniuskas, The Transforms in Signals and Systems. It's a really great book. There's only one copy in the library as far as I know, and I bought my own because I really liked it, because it has these really beautiful three-dimensional pictures. I mean, these are probably the best 3D pictures I've ever seen. So, for example, this is how he explains the Fourier transform, inverse transforms and so on. So you have to spend a lot of time understanding the figures, but when you get it, it's really, really nice. Now, Peter Kraniuskas was an engineer, and so he just says, yeah, we're going to scale it by j, and we get the dual property, and that's basically what I used it. However, when I looked through several different books, none of the other books talks about time scaling with a complex factor. So as I mentioned in my notes, I don't know, this is what I use. It looks reasonable. If you go through the proof and you use complex numbers, it looks reasonable that you can do it, but maybe there's some pathological cases. In any case, if you do go from first principles, then you can get the scaling. You don't have to use scaling property, and you can actually derive the second form that's in my answer by going from first principles. So anyway, just wanted to point that out. So in this case over here, A is assumed to be a real constant. I haven't checked whether it should work for a complex or not. In all practical systems, which is what we are interested in, we're going to have A as being a real constant. We're never going to have a complex quantity. We're just going to scale by reals anyway. Okay. Let me see. Now I'm trying to remember what the homework question. There was a homework question. Wait, what was it now? I forgot to write it. Does anybody remember what was it? The Laplace transform of what was? Yeah, that's right. Yeah, sine of k omega. Sorry, k omega t. Right. Yeah, I got it. Yeah. Right, ut. So we wanted to do this. So the ut is just to make sure that it's positive. We're not looking at the right hand side. So sine k omega t. So sine omega t. So maybe I'll I'll do the sign and then I'll solve the answer after that. So I just want to remember that. Okay, so I'll come back to that. Okay, let's do the time shifting. So time shifting basically says that x of t minus t naught. So we are shifting the thing over to the right by t naught, and that corresponds to e to the st naught. And this is very similar to the Fourier, where we multiply by j omega t naught. We're going to multiply by e to the st naught. So that's time shifting. And then the frequency shifting is very similar. We have e to the at xt it corresponds to x of s minus a. Okay. Now, in all these, I'm leaving out the region of convergence. The table you have in your notes has the regions of convergence, and so you have to be careful about those. But again, in most practical systems, we don't have to worry too much about the regions. They are quite normal. The next three are pretty important, so I'm going to go through them a bit more carefully. So the first one is differentiation. Okay, so differentiation basically says, and the transform is that d to the n xt by dt to the n, and the transform is s to the n xs. Okay, so this is really beautiful, and the reason it's beautiful is because what we're saying is that here is a differential equation in the time domain, okay, and we made it into just a polynomial in s to the n, right? So I can look at something that says, you know, if you remember the standard form for a linear LTI system, right? Linear time invariant system. It's something d to the n y, and we had this something like d to the n by d okay, y t plus d to the n minus 1 yt by dt to the n plus etc. equals d to the m x t by dt to the n, etc. So there's some, and ignoring the constant factors. This is a complicated differential equation, right? And what we did was we said, okay, we'll convert this into the d operator, and we use d to the n plus d to the n minus 1 plus etc. Okay, and we kind of had to go into that functional form, okay, and use the d operator. With the Laplace transform, that goes away. All we need to do is to just literally s becomes the d operator, and so we get a polynomial in s, and that's easy to do. And that's one of the beautiful things we get from the Laplace transform, and that's why we like to do Laplace transform, because you can convert systems of differential equations into systems of polynomial equations. And finding roots in polynomial equations is straightforward. Okay, you can do it by factorization, whereas finding solutions for differential equations is quite hard. So this is something that we really like to do. I'm going to write this stuff for integral, and then I'll stop. The integral is more or less the opposite of this. Integration basically says that integral minus infinity to t xt dt equal the transform is going to be xs by s. And so if you multiply by s, you're differentiating in the time domain, whereas if you integrate on the time domain, you just divide by s, okay, in the frequency domain. So again, this takes integral differential equation, which has both integrals and differentials, and makes it into this polynomial equations, and that is much easier to solve because we're just multiplying and dividing by s. Okay, so this is great because now we can do time shifting, which is multiply by e to the st naught. We can do frequency shifting. So why we don't do frequency shifting? Remember, I had this pulse, which was in omega positive and negative. I want to frequency shift it. I want to put it at some other center frequency. No problem. All I need to do is, if I want to shift it by A, okay, I just multiply by e to the at, okay, and that gives me the time signal. Right? I told you that I want to put a pulse in the frequency domain at, let's say, 2.4 gigahertz. Right? So that means this one A is 2.4 gigahertz, 2.4 into 10 to the 9. So I'm just going to multiply by 2.4 gigahertz, 2.4 10 to the power 9 t, that and multiply by xt, which is the sync function, and that tells me what signal I need to give on the time domain so that I'll have a frequency limited pulse in the frequency domain. So I can do the frequency shifting, the control knob. I can do time shifting, so I can change the position in time, and I can convert differential equations and integral equations into polynomial equations. So all of this you're getting from Laplace. Yeah?
Is there a reason why, or an intuition why in the integration the upper bound is t?
Why the upper bound is not, it's not plus infinity over here? Okay, so I don't have a good intuitive explanation for it. Okay, this is what we have. I mean, this is the mathematical form. It's sort of saying I'm taking the total amount of energy from negative infinity until now, whatever right now is, that's t, and that corresponds to the excess by s. Yeah, I'll have to dig some more for that. Okay. Convolution. So convolution is again the third nice property we have, and convolution basically says that if we have x1t convolved with x2t, the Laplace transform is the product x1s, x2s. And so what we're saying is that we're able to convert convolutions into products, and which is great because now we can we can take a LTI system and we can figure out its output by just product. So this actually is even nicer than it looks for the following reason. So let's say I have over here some system which is given by h1 of s, and then I have another system given by h2 of s, okay, and it has some input over here, and that input is, let's say, x1 of x of t, whose x of s, okay, is transformed as x of s. So, and let's say the output of the first system is the input to the second system, okay. What happens then is something very nice. The output of this system we know is going to be basically the convolution of xt and h of t, which is going to be xs h1 of s, and that's the input to the second system. So the output of the whole thing is going to be basically h1 of s, h2 of s, x of s. So we can take a system that may be quite large and break it up into little boxes, and each box we compute the Laplace transform separately, like so. And then to find the output of the whole system, we simply multiply the Laplace transform one after the other, and then we get the output over there. And that's very, very clean. And this is what in control theory we'll call a block diagram, system diagram. There are other words for it. But intuitively, this is what's going on, and this is happening because of the convolution property. Okay, so this is one of the key reasons why we go into Laplace transforms. Again, why is it? It's because, in some sense, what the Laplace transform is doing is to convert everything into these complex exponential sums, or in this case, complex exponential integrals, and so the convolution becomes products. So anyway, we have this property over here. So let's see. So the thing to remember is differentiation is multiplication by s, integration is division by s, and convolution is just a product of this one over here. Now the other, we don't actually have duality in Laplace transform because of the region of convergence. So we, in the Fourier transform, there's no issue region of convergence. In Laplace there is, so we don't get the duality property like we wanted, but we do have property that is sort of the symmetric property. So time shifting, frequency shifting, differentiation, integration, convolution, well, this convolution in the time domain, and we can do the opposite, which is multiplication in time domain becomes convolution in the frequency domain. So if I take two functions, x1, x2, x1 t multiplied by x2 of t, and this becomes x1 s convolved with x2 of s. So what's easy in the time domain is hard in the frequency domain. What's hard in the time domain becomes easy in the frequency domain. So this is actually, it's 1 over 2 pi, sorry, 2 pi j. So what's going on is that we can use this property sometimes when you find something really complicated. It's convolution in the transform domain. We'll go back into time and domain by doing the inverse transform and do all the simplifications in time domain, and then we can go back into frequency domain if we want to by taking the Laplace again. So this is a trick that we'll sometimes need to employ, not in this course, but it comes up later. Okay, any questions about this over here? So this is nice symmetric thing over here. What's convolution and multiplication become interchanged in these two domains. Okay, the last thing is actually a theorem. It's not really a property. And I should add that this is a so-called final value theorem. And the final value theorem is, of course, the asymptotic value rather than the final value. And it says that the limit t tends to infinity xt is given by limit s tends to 0 of s x of s. And so this is really useful because if I'm giving you a system, I can find if I find the Laplace transform, I can tell you its asymptotic behavior. So in control theory, what we'll do is we'll figure out what the system's transform looks like. How do we do that? By doing this over here. We'll break it up into boxes and compute the Laplace transform of this whole thing. Okay, so this is the Laplace transform. So I want to know what the system is going to look like as t tends to infinity. Instead of doing that, which can be complicated, all I need to do is just multiply by s and look at the limit at s tends to 0, and that will tell you what the behavior is going to be. So this is a very nice theorem, and that actually is what one of the homework problems was all about. And so here in that problem, I think I was saying, what is the behavior? So the system described by 5 over s plus 10 over s squared, I think. 10s squared, thank you. It doesn't matter, okay. And you want to know what is the asymptotic behavior. What happens as t tends to infinity? So what we do is we multiply this by s and take limit s tends to 0. And this is going to be just 5 plus 10s cubed. So this one becomes 0. And so we just have the value is going to be 5. So in the limit, it's going to converge to some value of 5. So what it sort of looks like is that the system is going to be in time, and this is the value 5. So the behavior is going to be something, we don't know what it is, but eventually it will asymptote to 5 like that. And so eventually in the limit, it's going to be 5, and that's what the system is doing. So if somebody says, what is the steady state behavior? It's another way of saying asymptotic behavior. It says, eventually it's going to settle down to 5. Okay, so and so we'll see physically what this means later on, but this becomes what's called the transient response. This is the transient. It goes away, and then this is actually what's determining it. So everything here is a transient. Okay, so you're pushing something, and it gets pushed. Eventually, it takes a while for it to reach the value, but when it gets there, it stays at 5. And that's what the system is doing over here. And we get that again from the Laplace transform without much work. Okay. Any questions about that? Okay. And so we'll see the final value theorem quite a few times in control theory. So that's why I put it over here. Okay. So with this, we sort of have the tools to do a few things, which is given a set of table of transforms, we can apply these different things, linearity properties, linearity, multiplication, differentiation convolution, and to obtain what we really want, right? So if we had this, in this case, 5 over s plus this, we had linearity we applied, and we said, okay, we can just take separately, one of them goes to 0, and that becomes really easy to do. I wanted to show a few things in this table of transforms, just because this will be useful. So one is a delta, it gets to 1, and then there's sort of a nice progression. The unit goes to 1 over